Another type of aqueous ionic equilibrium involves the formation of a complex ion. So we know a complex ion consists of a central metal ion that is covalently bonded to two or more anion molecules called ligands that are surrounding it, right? Same as we saw in chapter 19, and the same Lewis acid-base adducts that are formed just like we saw in chapter 14. So when a salt dissolves in water, a complex ion forms, with water usually as the ligand around that metal, similar to what we saw with FeH2O6, 3 plus Mysterio, right? Another complex ion with water as a ligand. But in many cases, when we treat this hydrated cation with the solution of another ligand, the bound water molecules are replaced by that other ligand. So let's get into one of the biggest examples, which is NH3. When a hydrated metal cation is now mixed with NH3, it is going to form an ammoniated ion instead of a hydrated. Why? Because NH3 is better at donating a pair of electrons. And thus it will replace water, and of course water is produced here. Now to simplify this overall expression, we just say M2 plus instead of including water so that we can show that the metal and the NH3 has formed its complex, okay? Now, once you have formed a complex and we're in equilibrium, guess what, folks? We get a new equilibrium constant. And that new constant is called the formation constant. And so for the formation constant is going to be set up just like we have everything before. You're going to have your products divided by your reactants. So your products is your complex divided by your reactants here, and that's how you get your Kf expression. So just like we saw with slightly soluble compounds, they all had that Ksp value, right? Well, with the formation or any kind of formation of complex ions, they will all have that Kf value. So you can have many complex ions like we see in this table. Everything's still going to be at 25 degrees Celsius. And here are the formation reactions now. And each formation reaction has its own Kf value. And of course, with the Kf value, you can go ahead and write the Kf equilibrium expression. Now, that means when you're starting calculations, you need to create your formation reaction, and you need to go ahead and create the expression for Kf. Let's get an example of creating a formation reaction. So here we have Cr NH3 3 plus, and we need to create a reaction to show how this is formed. So the first thing you want to do is figure out what the ions are here. And of course, we're talking ligands as well. So we know we're going to have Cr3 plus, which we see here, and 6 NH3s, which we know are our ligands. So we need to show this in a formation reaction. So let's go ahead and write this out. The first thing you want to do is write your complex ion, which is being formed as your product. So I have my Cr NH3 6 3 plus. This is my product. I know we're going to be in equilibrium, and now I need to have my ions on the reactant side, and they need to be balanced. With my formation reaction complete and everything is balanced, I now can go ahead and get my formation constant, and my Kf is going to equal to my products divided by my reactants. So I have Cr NH3 6 3 plus as my products divided by Cr3 plus as one of my reactants, and then NH3 raised to a power of 6. Now I can go forward and use a Rice table if I need to. I can go forward and solve for Kf for any one of these equilibrium species. It's just like every other equilibrium calculations we've been doing. Same old when it comes to assumptions. Let's go ahead and get into an example. This says we're going to be calculating the concentration of a complex ion. Now, an industrial chemist converts ZnH2O4 2 plus to the more stable ZnNH3 2 plus by mixing 50.0 liters of a 0.0020 molar Zn2 plus and 25.0 liters of a 0.15 molar NH3. What is the final Zn2 plus concentration at equilibrium? The Kf of ZnNH3 2 plus is 7.8 times 10 to the 8th. So first, we definitely need to create the formation reaction for ZnNH3 2 plus. And then, of course, we need to get the Kf expression. And then, if you start thinking about it, you say, hold up, we are mixing things together here. Because we're mixing things together, that should automatically start telling you that we have to start figuring out some initial amounts. We're probably going to have a new total volume. All those little details are coming back when it comes to solving for equilibrium problems. So let's just do things step by step. So first, I definitely got my formation reaction, right? So again, we're trying to form this complex ion, ZnNH3 2 plus. So I have to write down my ion for my metal first, which is Zn2 plus, and then I just make sure I balance the number of ligands, which is just 4NH3. So I just set that up on the side. I also got my Kf expression, which is going to be my product divided by my reactant. And then I went further and got my, my total volume and stuff like that. So first for the total volume, I took 50.0 liters plus 25.0 liters, and I got a total of 75.0 liters based on what was given. And then, because I know they gave me molarity and volume, I went ahead and got my moles of Zn2 plus. Once I got my moles of Zn2 plus, I got my moles of NH3 because I knew that I'm going to be mixing two new volumes. And so therefore, I'm going to have a brand new initial concentration. So I first get my moles, and then I divide it by the total volume, and that gives me the initial amount that I can move forward to using my Rice tables. And so to get the moles of Zn2 plus, I took 50.0 liters times the concentration given, which is 0.0020. I got 0.10 mole. For the mole of NH3, I took 25.0 liters and multiplied it by 0.15 molar. I got 3.75 moles. To get the initial concentration of Zn2 plus and of course of my NH3, I took the moles and divided by the total volume. So here was 0.10 moles divided by 75.0 liters, and I got 1.3 times 10 to the negative 3 molar. For the concentration of NH3 initially, I got 3.75 moles divided by 75.0 liters, and I got 5.0 times 10 to the negative 2 molar. With these new initial concentrations, I plug them directly into my Rice table. I have my formation reaction here. I have 1.3 times 10 to the negative 3 initially for Zn2 plus, 5.0 times 10 to the negative 2 for NH3, and of course 0 for my product. Now, before I start writing in minus X and everything like that, I have to look at my Kf expression and value. My Kf value is very large. It's 7.8 times 10 to the 8th. When you have a large Kf value, that means that you're going to have mostly this complex form, or mostly products, right? And so because we're forming this complex, we definitely are going to be assuming that all of our Zn2 plus is going to be used up to form that complex. Why are we focused on Zn2 plus? Because as you can see, our NH3 is definitely in excess here. And so Zn2 plus is going to be our focus, is going to be used all up. So now we have to think, wait a minute, they want us to find the final concentration of Zn2 plus. So isn't it going to be super small? Isn't it going to be negligible? Well, it might be negligible, but they still want us to find that value. And so I automatically set this as X. And because this is X, that means instead of writing minus X here, that means Zn2 plus would have to be used up in some way so that we can solve for, of course, our other equilibrium value. Once we have our other equilibrium values, we can plug them into our Kf expression and then solve for Zn2 plus at equilibrium like the question asked. Okay, so we have 1.3 times 10 to the negative 3 minus 1.3 times 10 to the negative 3 is now equal to X, not 0. Is the number going to be super small? Yeah, but the question still wants that number. Okay, next we're going to have 5.0 times 10 to the negative 2 minus 4X, which is 4 times 1.3 times 10 to the negative 3. And of course, for our product, it's simply going to be plus 1.3 times 10 to the negative 3. So I'm going to go ahead and subtract these two numbers to get our equilibrium amount. Okay, so I took my 4 and I multiplied it by 1.3 times 10 to the negative 3, and I got 5.2 times 10 to the negative 3. So when I take 5.0 times 10 to the negative 2 and subtract it from 5.2 times 10 to the negative 3, I get 4.5 times 10 to the negative 2. And just to reiterate, this is not 0, right, folks? And some people might say, well, I don't get why it's 0, because sometimes we have made the assumption that it's 0 when we're dealing with like strong acids or strong bases, for example. But when we're dealing with things in equilibrium, remember, nothing is truly going to be 0. There's always going to be things in equilibrium, so we're expecting that even if it's just one single ion of Zn2 plus, it's still floating around, and that's what we want to capture. Okay? Now for the complex ion, we already know it's still going to be 1.3 times 10 to the negative 3. I'm going to now take my Kf expression, which I put here, and I'm going to solve for the variable they're looking for. They want Zn2 plus. We already have all of our amounts here. So I'm going to cross multiply. So I can replace Kf with the Zn2 plus, and therefore my Zn2 plus is now going to equal to whatever the value I have for my complex ion divided by my Kf value and whatever value I have for NH3 raised to a power of 4. We already know those values here, here, and here. So let's go ahead and plug them in, folks. So now plugging in my complex ion amount at equilibrium is 1.3 times 10 to the negative 3. My Kf value is 7.8 times 10 to the 8th. and my NH3 value is 4.5 times 10 to the negative 2, and I have to raise that to a power of 4. When I raise this number to a power of 4, I get 4.10 times 10 to the negative 6. I then am going to multiply that by 7.8 times 10 to the 8th. I get 3.198 times 10 to the 3. I then take 1.3 times 10 to the negative 3 and divide it by this number, and I get 4.1 times 10 to the negative 7 molar as my final answer. So again, very similar to the type of equilibrium problems we've been seeing in these last couple of chapters, right, folks? It's all about having a strategy and being able to just layer in this new information. But you really cannot layer in new information if you don't have a good foundation from before. So again, that's why it's very important for that review. All right, on to the next concept.